That works for you. Thanks, Liz. All right, arrangements in a circle. So what we just practiced. When objects are arranged in a circle, the number of arrangements is reduced. That's what we just discovered, because it's the same. Every time you move around that circle, you're still in the same order. You just move one spot to the left. 4 people, if you were putting you in a line, can be arranged in 4 factorial ways. But with a circle of arrangements A, B, C, and D, it is the same as the arrangements B, C, D, and A. We're just changing which letter we're starting with as you move around that circle. All we discover as the waiter or the observer, all we have to do is move one position and we have exactly the same arrangement as the first. So, a circle does not have a beginning. So it is necessary to place one person into their seat and then arrange the other people as though they were being ordered in a line. So for 4 people to sit down in one arrangement, we arrange the others in 3 factorial ways. Now, when we were up here before, this is how I like to think of it. If we had 6 people, there's n number of people that we're putting around a circle. If we're putting them in a line, we would say that is n factorial ways of putting you in a line. But because there was the 6 different places that you could all be the same, or the n different ways as you moved around that circle, we would divide that by n. Now we know, because we like to unroll things, we could unroll that top factorial to be n times n minus 1 factorial over n, and the n's would cancel out to get simply n minus 1 factorial. Okay, so that's how it works, in that if I have 6 people, it's actually only 5 factorial. You take one off and it's 5 factorial if you're putting them into a circle rather than a line. Yeah? So that's your formula, kind of, that one there. N minus 1 factorial is how you put a certain number of people in a circle.
So the first one would be 5 factorial over 5.
Yeah, so 5 boys are to sit around a circular table. In how many ways can this be done if there are no restrictions? So I'm going to choose the yellow highlighted one though, okay? So I would go, there's 5, so it's 5 minus 1. You can write, all right, I'll do the whole thing. 5 minus 1 factorial, or just 4 factorial. Okay? And you'll probably find you'll go straight to the 4 factorial. You'll go, it's a circle, I'll just take one off. Okay, if 2 of the boys are not allowed to sit together. Okay, so there could be 1 chair between them, there could be 2 chairs, 3 chairs.
They can't sit together all on the ends.
It's a circle.
There's no end.
It's a circle, so there's no end.
Would you subtract it?
Yes. Whenever you're saying 2 people shouldn't be together, make them together and subtract it off the total. Okay, so if we put those 2 boys together, so sit boys together, they form one group. Okay, so I had 5 groups. I'm now down to 4 groups because they're being paired together in one group. But I'm putting them in a circle. So when I'm putting 4 groups in a circle, I'm doing what? 3 factorial. So there's 3 factorial ways of putting those 4 groups around a circle. However, there's 2 boys, and the order those 2 boys sit in is different. So we'd have to times that by 2 for the different, or 2 factorial, which is 2, to do the 2 possible ways that they could be sitting next to each other. So there is 12 ways of them sitting together, which means, therefore, the boys sit apart in, the total was 24 that we worked out in part A, and I subtract off the 12, which means it's 12 again. So there's actually half of the ways of them sitting together and half of them not.
Just a coincidence.
It was a coincidence, just because it's the number that was chosen.
So it's 50-50.
It is, actually. And that wasn't a probability question, okay? So that's it. We're finished with that. Example 2. In how many ways can 4 men and 4 women be seated around a circular table if there are no restrictions? Okay, so the 4 men and 4 women part, that's not important here. We have 8 people. That's all we have to worry about. There's 8 people for this starting part. So I just want to put 8 people around a circle. Subtract 1, right? So 7 factorial ways of doing that, which is 5,040. If the men and women are seated alternatively, so that means boy, girl, boy, girl, boy, girl. Now, this is where you start having to place someone first because you don't know where they're going to start, okay? So we place a man. We'll start with the boys, okay? So we're going to choose one spot for the man to sit in. He's going to go, whoop, one spot. Now, it doesn't matter. I mean, I know there is 8 spots around there, but if he's the start of the circle, then it's the same order. Does that make sense? Yeah? All right. Then I want to sit the rest of the men. Because I now have a starting point with that first man, there are 3 factorial ways to arrange the rest of them because I gave myself a starting point. That's basically just arranging those 4 men in a circle, isn't it? 4 men, 3 factorial ways. However, when I do the women, because those men are already seated there, yes, 4 factorial, okay, because where the men are sitting is going to affect the order each time those girls switch around. Okay, so 4 factorial for the men. Women, thank you. So to fit the women in the gaps, so that's 144 ways. If you want an explanation, so you can put, this is fix first man, just explain what we've done. Fix first man. All right. Sit the rest of the men around circle. And then arrange women in the gaps. Okay, just when you look back to know how we got those numbers. 2 particular men are not to sit together, so obviously we're going to make them sit together. Yeah. Okay. So sorry, what was that, Isaac?
Would it be 6 factorial times 2?
Yes, correct. So for everybody else, we have our 8 people. We're not worried about the men and the women being alternating anymore. It's just we have our 8 people, but 2 of them don't want to sit together. So we now have 7 groups. We're making them sit together, 7 groups. So to arrange them in a circle means 6 factorial times by 2 because those 2 men can switch places. So that is how we sit 2 men together. That is 1440 ways. That means, therefore, we want to find the ways of them not together, which means we subtract it from the total. So our total was 5,040. Subtract the 1440.
600.
Thank you. Okay, next page. Arranging groups in a circle. So we did have a couple, in those questions there, we did have people making a group, but the groups can get a little bit more complicated. So just a reminder here, first of all, choose an order. So you have to order the people in the groups and then arrange them around the circle. Actually, it doesn't matter which one you do first. You can arrange them around the circle and then order the group, which is kind of what we've been doing, but you have to order both parts. So let's practice this last, or actually no, we've got 2 more to do. 2 more examples. Example 3. 5 girls and 5 boys are sitting around a table. Sounds very similar to what we were doing before. How many ways can this be done if there's no restriction? Always like to start with that, so we have our total.
9.
That's right, there's 10 people, so we do 9 factorial. Excellent. So 362,880. Okay, we did a question like this next one as well. Let's see if we can remember how to do it. The boys and the girls alternate.
1 times 4 factorial times 5 factorial.
Correct. So we place one of the boys, and then there is 4 factorial ways to arrange the rest of the boys, and then we multiply by 5 factorial for arranging the girls in the gaps between them. Okay, order being important there. So 2880. Okay, part C, this is a new type of question. There are 5 couples who want to sit together. So 5 couples, so instead of having 10 people, we have 5 groups.
1 times 4 factorial.
Yep, so we have 1 times 4, oh, you can just go 4 factorial. So there's four factorial to arrange those 5 groups in a circle, but
We still have to do times 2 because
not just once.
Times 2
Times
to
10.
be 4 or something.
Each of those groups has 2 for each of them, and there are 5 groups.
Times 2 to the
times
4.
2 to the 5, because there's 5 groups.
Oh, what?
Okay, so you could go 2 for the first group, 2 for the second group, 2 times 2 times 2, or 2 to the power of 5 is much shorter. So each of those 5 groups can be switched around in 2 different ways.
7, 6.
Excellent, yeah. Okay, D. The boys all sit together and the girls all sit together. Effectively what you are doing then is you're cutting your circle in half and we're lining the boys up one side and the girls up the other side. It kind of destroys our circle in terms of how we arrange them, right?
Like we have 2.
So we're putting the boys in a line on one side, which is 5 factorial ways, and we're putting the girls down the other side of the circle in 5 factorial ways, and that makes 1, 4, 4, 0, 0.
But the girls can sit on that side and the boys can sit on that side.
But it doesn't matter where the start is, does it? Because every time we rotate them around, it's still the same number of ways.
Oh, okay. So we know the order for this one.
Yeah.
It's a separate.
It's because we've got boys and girls separated, they're effectively lining both sides of that circle. And it doesn't matter, as I was saying to Jess, it doesn't matter how many times you rotate that circle around, it's still boys and girls making half the circle each. Yeah? All right. E. This is the fun one. Look at the space I left for it. Okay. 4 couples sit together, but the 5th have broken up and want to make everything complicated.
Everybody, right?
Yeah. They wish they were in here. They want to be in here doing extension
They're
maths.
doing standard.
Yeah. So 4 couples sit together. The 5th couple have broken up and refuse to sit together.
Oh no.
Okay. So we have 4 couples and we have 2 singles. So we have 6 groups.
Uh-oh.
All right. So let's write that down. We have 6 groups. But, okay, I'm going to draw a little diagram for this. How can we sit these people? I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I think I've got 10 crosses all around there. So the broken up couple, they're the ones causing the difficulty, right? So let's focus on them first. First of all, I'm going to fix the first single person. Okay, so I'm going to lock them in. They're going to choose their spot. I'm writing some explanation down as we go, but I'll do the numbers down the bottom here. So I'm fixing that first person. I'm going to pick one seat for them. This is their spot here, right? I'm fixing them right there. Then I want to choose where the ex-partner can sit. Now, the ex-partner cannot be sitting next to them, but because the other people also have to be in pairs, so can't be sitting on those 2, because the other people in pairs, they can't be sitting there or there either, because we need to have a couple on either side of that one person, right? So I could put them, what symbol am I going to use here? I could put them here, or I could put them there. That's 2 options. Or I could have put another couple here and another couple there and sat the ex-partner right opposite.
3.
Okay, so there is 3 different ways the ex-partner can be seated. Now, the only way we really could do that was by visualizing it, okay? Because we had to think of where those other people were sitting. No, we just literally counted 3 ways for them to sit, so just times by 3. All right, then we have to worry about our couples. So we have our remaining couples. There are 4 couples. Because we've already got a fixed start point, how many ways can I arrange those 4 couples? 4 factorial. So I'm going to times that by a 4 factorial there.
Times 4.
That's right. Very good. Okay, so I'll keep writing my instruction down. So each couple can be arranged in 2 factorial or 2 ways. Okay, so I wouldn't expect you to write all those words down, but when you look back at it and go, why on earth did we do 1 times 3 times 4 factorial times, at least you could read through how we were thinking this problem through.
How is it each couple can be arranged in 2 factorial?
Because with those couples sitting together, there's 4 couples, remember? They're in pairs. So there's 2 ways. Who's first? Is it Tori then Jess, or is it Jess then Tori?
Yeah.
Okay, there's 2 different ways we could sit each of those 2 people.
But there's 4.
And there's 4 couples that we're doing that for. So 1, 1, 5, 2.
Do you minus the other total one?
No, we just wanted the number of ways of sitting that person apart. So that was it. That was it. That's the answer. And just because we did probability, we should do a probability question. So probability of arrangements around a circle. There are 6 people, let's call them A, B, C, D, E, F, to sit around a table. So there's your circle. What is the probability that person A will have person B sit immediately to his left and person C will sit immediately to his right? Now, that sounds super complicated, but it is telling you the order of those 3 people.
So it's already fixed 3 people.
That's right. So those 3 people, we don't have to arrange that 3 people in a group. They've already been arranged. So they are making one group.
1 times 6, 3 factorial.
How many groups do I have? So 1, 2, 3, 1, 2, 3, 4 groups.
4 groups.
Yeah, you already got 1 fixed.
That's right.
Which means times 3 factorial.
That's right. So what we've done is we're fixing A, B, and C. They're all fixed together. So the remaining people arranged in 3 factorial ways, which is equal to 6. However, this was a probability question, which means we need to know the total so that we can make our fraction. No restrictions at all. If I was putting A, B, C, D, E, and F, no, we're only going to F, in a circle, how many ways can I put 6 letters in a circle? 5 factorial ways.
Equals to 125 and equals to 6.
120. 120, you mean?
Oh, yeah. Memorize that.
That one we've done so many times, haven't we? Okay, so we can finally do the probability. Oops, I can't spell apparently. Probability. There was 6 favourable outcomes out of our 120, which simplifies to a 1 in 20 chance of the A, B, C sitting in their special arrangement. That's it.
Not bad.